Hello, I will now go through the 2006 Form B FRQs. There's six of them. Form B just means there's different versions of the exam. So this was an alternative version of the exam, but it's the same sort of question, has the same difficulty and everything. So it's still really good practice. And so here is six FRQs. So if you want to give these a try, like, pause the video and give it a try, and then I'll go through the answers. And so anyway, so there's six free response. The first five of them, they say you got to spend like 12 or 13 minutes each on each one. And then number six should take 25 minutes. Make sure and do the number six, please. Okay, so let's read this one. It says a large regional real estate company keeps records of home sales for each of its sales agents. Each month, the company publishes the sales volume for each agent. Monthly sales volume is defined as the total sales price of all the homes sold by the agent during the month. The figure below displays the cumulative relative frequency plot of the most recent monthly sales volume in hundreds of thousands of dollars for these agents. Cumulative relative frequency. You know what that means? That's right. It means percentile. So this is a percentile graph, and it allows you to estimate percentiles. And so here's the percentiles all the way from 0 to 100%, and it puts it in decimal form. And here's the monthly sales volume in hundreds of thousands of dollars. So in the context of this problem, explain what information is conveyed by the circled point. Well, the circled point, that would represent $300,000. And this would be saying that it's at the 40th percentile. So it's saying 40% of the agents sold at or less than $300,000. So that's what that is saying. 40%. It's at the 40th percentile. So 40% of this company's agents sold $300,000 or less in home sales for this month. So, okay. And that's all there was to A. So B, what proportion of the sales agents achieve monthly sales volumes between 700,000 and 800,000? So let's go. So you go use a straight edge, go to 700,000. Well, that would be up to 70th percentile, and 800,000, appropriately enough, is at the 80th percentile. And so the difference between the 80th and the 70th percentile is 10%. And so that's all there was to that one. All right, for the values between 10 and 11 there on the horizontal axis, the cumulative relative frequency plot is flat. In the context of this problem, explains what that means. Flat means there's no data there. So that what that means is there was no agents that sold between 900 or between a million and 1.1 million in sales. There were no agents, and so therefore it was flat. All right. So so that's what that is saying. So for part D, a bonus is given to 20% of the sales agents. Those who achieve the highest monthly sales volume during the preceding month will receive a bonus. What is the minimum monthly sales volume an agent must have achieved to qualify for this bonus? So he's got to be in the upper 20%. Well, the upper 20% means he's got to be in the 80th percentile or above. Well, the 80th percentile, as we've already discussed, that's over it right there. 80th percentile, and that goes down to $800,000. So $800,000 or above. So the minimum they could get would be $800,000 to qualify for that. So that means 20% of the values are above it. That's it. That's all there was to number one. So that means it's time for number two. So let's see if we can do number two. A large company has two shifts, a day shift and a night shift. Parts produced by the two shift must meet the same specifications. The manager of the company believes that there is a difference in the proportion of parts produced within the specification by the two shifts. To investigate the belief, random samples, that's a big deal to us, that prevents bias and gives us representative samples, evens out the influence of other variables. Random samples of the parts that were produced on each of the shift were selected. For the day shift, 188 of the 200 selected parts met specifications. And for the night shift, 180 of the 200 selected parts met specifications. All right. Use a 96% confidence interval to estimate the difference in the proportions of the parts produced within the specification. So just to write this down here. So it's for the day shift. Okay, our statistic, our p hat for day, we shall say, it's 188 out of 200. And so that's 94% or 0.94. And so for the night shift, So for the night shift, and they're going to give you a lot more room than this. They're going to give you a lot of room to answer the question, by the way, in the exam. So our p hat for night is 180 out of 200. And so that would be equal to 0.9. And so 4% or 0.04 would be our estimate of our difference. But anyway, so we are going to, whenever you make a confidence interval, you have to do the TAME acronym. So here we go. You have to state what you're doing. I'll create a 2 proportion Z interval. All right. And then you have to send, it says random sample is taken. So independent random conditions met. When it's 2 samples, you have to say independent random. There must be at least 2,000 parts in each shift for our sample sizes to be less than 10% of our population sizes. And n times p and n times 1 minus p for both samples have to be greater than 10. Now, n times p is just going to be 188 over 200 times 200. So it's n times p is just your number of successes, so to speak. N times 1 minus p is your number of failures for your first sample and for the second sample. They're all greater than 10, so normality is met. In other words, this sampling distribution of all possible differences is approximately normal. And so then we make our interval, which I did by hand here using the formula, the formula sheet. So every confidence interval is statistic plus or minus critical value times standard error. Now here we get 2 statistics. So the statistic is actually the difference between these two, okay? And then the critical value, that's going to be Z star. And then the standard error of the statistic, that's going to be in the next page. So standard error of the sample statistic for 2 proportions is that guy right there. That guy right there. And so that is, so that's the difference in the statistic. That's a critical value, which I'm going to show you how to do that in a second. And then there's the formula for the standard error. So to find the critical value, what you would go to your critical value table. Now this is a Z, but so the Z's are at the bottom of the table. And this said 96%. So you go to 96% and it's just the number right above it. There it is right there. So the critical value is 2.054. Now I used inverse norm in my calculator to come up with a more precise value, but you don't necessarily have to do that. But anyway, so let me show you how to use your calculator to do that. So to use your calculator to do that, all you've got to do is we hit the stat button. So we hit stat, we go to test, and this is a 2 proportion Z interval. So a 2 proportion Z interval is right there, option B. It's like the 12th option. And so we have 188 out of 200. Is that right? 188 is 200 in both, 200. And then we have 180 out of 200 like that, and 96% like that. Make sure those are integers, by the way. And so there's our interval. Now, and so there you go. So there's the interval. So anyway, so hopefully, yeah, I entered those right, didn't I? So yes, I did. Okay, good. So there you go. And then once you've made the interval, now all you've got to do is show the interval, by the way. You don't have to show your work, but you have to understand that because that could be another problem. So you'd say I'm 96% confident that that interval captures, and use the language they use in the problem, the difference in the proportion of parts produced within specification by the 2 shifts. So that's what I did. So it captures the difference in the proportion of parts meeting specification for the 2 shifts. All right, then it asks, based on this confidence interval, do you think the difference in the proportion of the parts produced within the specification by the 2 shifts is significantly different from 0? Well, 0 is in the interval, so it's a plausible value. So the answer to that question would be no. 0 is inside this interval, so it is a plausible value for the 2 difference, piece of D minus piece of N. And so that's that. And that's it for number 2. So let's talk about golf, which is something I'm very fond of. So number 3, golf balls must meet a set of 5 standards in order to be used in professional tournaments. One of these standards is distance traveled. When a ball is hit by a mechanical device called iron Byron, with a 10-degree angle of launch, a backspin of 42 revolutions per second, a ball velocity of 235 feet per second, and the distance the ball travels may not exceed 291.2 yards. Manufacturers want to develop balls that will travel as close to 291.2 yards as possible without exceeding that distance. A particular manufacturer has determined that the distances traveled for balls it produces are normally distributed. Okay, that's a big deal to us. With a standard deviation of 2.8, but they're not telling us the mean. That's weird. Okay. This manufacturer has a new process that allows it to set the mean distance the ball will travel. If the manufacturer sets the mean difference equal to 288, what is the probability that a randomly selected ball for testing will travel too far? In other words, greater than 291.2. And so we'll say that's just normal CDF from 291.2 to infinity with that mean and that standard deviation. I get that. Now, I like always to draw the curve. So this would be fully showing your work. Make sure and label each of those numbers, lower bound, upper bound, mu, and sigma. You may be asked to draw the curve to show the mean and standard deviation and to show your X value, 291.2, and to do the proper shading. So, so there you go. And so that's how you do that. And that's your answer right there. Now, normal CDF, just let me remind you, you would say second VARS, which is distribution, normal CDF. Then we're going from 291.2 to infinity. You can just put like 9 billion, and then 288 and 2.8. So this is just a stock normal CDF problem, and there it is. So it would happen about 12.5% of the time. All right. So assume the mean distance traveled is 288 and that 5 balls are independently tested. What's the probability that at least one of the 5 balls will exceed a maximum distance of 291.2? All right. The easiest way to do the probability of at least one, it's going to be 1 minus the probability of 0, because the thing about it is, all right, the number of balls that would exceed the distance, it could, if you do 5 balls, you could have 0, 1, 2, 3, 4, or 5 that do it. So the probability of at least 1 would be all that. So then that has to add up to 1 or 100%. So if we find the probability of it happening 0 times, then subtract it from 1 and we'll get it. So the probability that it's going to happen 0 times is just going to be 1 minus that to the 5th power. Okay, 1 minus that to the 5th power, because that's the probability of success. Probability of failure is 1 minus that. So it's going to be 1 minus 0.508 roughly, which is that. And so that is in essence your answer. And Coach Brinkley is disturbing me. So what do you want?
Is it okay if I use your room tonight for night school?
Yes, as long as you leave me alone like for five seconds from now. Okay. All right. So then on part C, it says, if the manufacturer wants to be 99% certain that a randomly selected ball will not exceed the maximum distance of 291.2, what is the largest mean that can be produced in the manufacturing process? All right. So what we would do there is we don't know what the mean is, but we know that this is at the 99th percentile. So what we're going to use is we're going to use a formula that has the mean in it, and that's the z-score formula. Z is equal to x minus mu over sigma, like that. And so we'll use that formula. We just need the z-score. Well, the way you find the z-score is by doing inverse norm of your percentile with a mean of 0, standard deviation of 1 to get that, okay? And so we then plug that into the formula for z-score, okay? And so, of course, inverse norm, let me remind you. So inverse norm, and that would be 0.99, mean of 0, standard deviation of 1. So that's the z-score. We use that, and so we take that and then solve that for mu. Just go that times 2.8 is equal to, and subtract 291.2, and so it ends up being that. And of course, it's minus that's equal to that. So there it is. And so that's how you do that. And that is how you do the number 3 problem. Okay, so we're halfway done. So here we go. Number 4. So this one says, the developers of a training program designed to improve manual dexterity claim that people who complete a 6-week program will increase their manual dexterity. A random sample of 12 people, okay, that's good. Now we can generalize about all people from which we got that random sample, enrolled in the training program was selected. A measure of each person's dexterity on a scale from 1, the lowest, to 9, the highest, was recorded. just before the start of and just after the completion of the 6-week program. The data are shown in the table below. All right. And so this is what their dexterity was before the program, and this is what their dexterity was after the program. So can one conclude that the mean dexterity level for people who have completed the 6-week program, training program, has significantly increased, and support your conclusion with appropriate statistical evidence? That means do a test. That's what that means is. Now you notice this data is paired. You have these, this number goes with this. Whenever the data is paired like this, we are going to do a paired t-test. And so what we'll do is we'll subtract these numbers, and I'm just going to say after minus before. You could go before minus after. You would reach the same conclusion, but I'm just going to go after minus before. So I subtracted all these numbers, and I got these differences. So that'd be 7.8 minus 6.7 is 1.1, 5.9 minus 5.4 is 0.5, and so forth. And so I found these differences like that. And so then we have to do the THAME acronym to do our test. So this is a paired t-test for a mean difference. The null hypothesis is that there's no difference. Okay, where mu sub d is the mean difference for after minus before for the dexterity scores. The alternative is greater than, because if we're expecting the after to be, it says has significantly, the dexterity has increased. And if that's the case, if it's increased, then the after should be greater, and this should be greater than 0. And we then sin. It says a random sample was taken, so random conditions met. There must be at least 120 people like this for our little n to be less than 0.1 times our big N. All right, then we have to check normality. The sample size isn't bigger than 30. All right, so that doesn't work. It doesn't say anywhere the population varies normally, so that doesn't work. So we have to graph our differences. So I just graphed those numbers on a little dot plot. There's no outliers or strong skewness, or normality is reasonable. This is sort of close to an outlier, but this is okay. And so then we find our t-test statistic. Okay, statistic minus our parameter, which is the hypothesized value of 0 there. Okay, and then S over the square root of N. So that's just our formula here for this. So our formula is going to be statistic minus parameter over standard error, like that. So our statistic is, in essence, the mean of our values minus that, and then the standard error is S over the square root of N. Now, so you don't have to show your work here. You have to be able to recognize that formula, but let me show you how to quickly get these numbers. You're just going to put these numbers in list 1. So I'm going to go stat and edit. So in list 1, I'm going to put all these numbers. So 1.1 and 0.5. 0.6 and 0 and 0.7 and 0.5 and 0.5 and negative 0.1 and negative 0.1 and 0.5, like that. So, and let's see, negative point, and then also 0.5 and 0. So 0.5 and 0. And so then what you do is you just go stat, test, and t-test, like that. And we entered data just then, or at least I did. The null hypothesis value is 0, no difference. List 1, the alternative is greater than, and so there's my test statistic p-value, so test statistic p-value, and anytime you have a t, the degrees of freedom is sample size minus 1. So this p-value is less than 0.05. So I reject an all. There's convincing evidence that, and then use their language, that the mean manual dexterity for people who have completed the 6-week training program has significantly increased. So that's what I wrote there. So there you go. And so that's how you do number 4. That would be a t-test. Okay. So now let's do number 5. So we get number 5. All right. When a tractor pulls a plow through an agricultural field, the energy needed to pull that plow is called the draft. The draft is affected by environmental conditions such as soil type, terrain, and moisture. A study was conducted to determine whether a newly developed hitch would be able to reduce the draft compared to the standard hitch. A hitch is used to connect the plow to the tractor. 2 large plots of land were used in this study. It was randomly determined which plot was to be plowed using the standard hitch, As the tractor plowed the plot, a measurement device on the tractor automatically recorded the draft in 25 randomly selected points in the plot. After the plot was plowed, the hitch was changed from the standard one to the new one in a process that takes a considerable amount of time, substantial amount of time. Then the second plot was plowed using the new hitch. 25 measurements of the draft were also recorded at randomly selected points in the plot. All right. What was the response variable? Identify the treatments and the experimental unit. So this is a weird experiment that deals with hitches and plows and these two plots. Okay. So, so a bit of terminology. So the response, how are we? So we want to see if this new hitch is better than the standard hitch and how are we judging that? And that is by the draft, and the draft is basically, the force that is required to pull the plow through the dirt. Okay. So the response variable here is the draft. The treatments are what we are in essence randomly assigning to our units is the new hitch and the standard hitch. That's what we want to see whether or not it works. That's what we want to compare. The experimental units are whatever is receiving the treatments. And what is receiving the treatments? And it's the two large plots of land. That's what is being randomly assigned to. The hitches are being randomly assigned to the two plots. So that may be a bit confusing, but that's what it is. All right. Given that the goal of the study was to determine whether a newly developed hitch reduces draft to the standard hitch, was randomization used properly in this study? Well, yes, it was used properly because the hitches were randomly assigned to the two plots. And that's it. I mean, so yes, they were randomly assigned. There was just two of them, but they were randomly assigned to the two plots. Part C, given that the goal of the study is to determine whether a newly developed hitch reduces draft compared to the standard hitch, was replication used properly in this study? Replication just means you have a large enough size. Here we do not. Okay. No, there were only two plots, one for each hitch. Replication would call for a large number of units. And so that was sort of one of the big problems with this. And then part D, plot of land is a confounding variable in this experiment, plain why. In other words, if let's just say the new hitch had worked a lot better and improved the draft greatly, a problem could be, there could be something different about that plot because there's just one plot. For instance, maybe the moisture in the ground is different in the two plots. There could be something different about the plots that affects the draft. Maybe one of the plots has more moisture than the other. Maybe it was this increased moisture that caused a different draft result, even though it appeared to be different because of the type of hitch. And so I've connected our three variables there: the type of hitch, the draft, and then the plot, the different plot. The moisture, in this case, the moisture in the plot. So, so that's number 5. That was a challenging experimental design problem, I shall say. All right, and number 6. So number 6 is it's going to be the longest question, and they encourage you to spend like 25, 30 minutes on it. So it's 1/4 of the free response grade. Make sure you answer each part of it as best you can. Okay. Sunshine Farms wants to know whether there's a difference in the consumer preference for two new juice products, citrus fruit and tropical taste. In an initial blind taste test, 8 randomly selected customers were given unmarked samples of the two juices. The product that each consumer tasted first was randomly decided on by the flip of a coin. After tasting the two juices, each customer was asked to choose which juice he or she preferred, and the results are recorded. Let P represent the proportion of consumers who prefer citrus fresh. In terms of P, state the hypotheses that this Sunshine Farms is interested in testing. Well, okay, so they want to know, is there a difference between citrus fresh and tropical taste? Okay, so if the null hypothesis is there would be no difference in the two, and it'd be 50%. So our null hypothesis is just going to be that P is equal to 0.5, and it just said difference. It didn't say greater than or less than, so it's not equal to. Ordinarily, we would define P here, but guess what? They already did that. They said let P represent, all that, and so they've already defined P. So there you go. Part B. One might consider using a one proportion z-test to test the hypotheses in A. Explained why this would not be reasonable. Well, we have a really small sample size here, 8. 8 is insanely small, especially for proportions. So the normality condition is not met, because for normality to be met, you gotta have n times p and n times 1 minus p greater than 10. And in this case, they would both be 4, and they're not bigger than 10. So that would not work. And by the way, you wouldn't do a 2 sample thing here, because in essence, you just have one sample. Okay, it's not, the proportion that like citrus fresh and the proportion that like tropical taste, because they are not independent samples. If this one is, 0.6, that one's got to be 0.4. Okay, so it's in essence just one sample here, by the way. Okay, part C, let X represent the number of customers in the sample who prefer citrus fresh. Assuming there's no difference in the consumer preference, find the probability for each possible value of X. Record the X values and the corresponding probabilities in the table. All right, so when you talk to 8 people, all right, the number who prefer citrus fresh could be any number from 0 to 8. Okay, and we're going to assume there's no difference. In other words, we're going to assume the probability they're like citrus fresh is 0.5. And so here is all the possible number that could like citrus fresh, 0 through 8. And the way you can find these numbers, this is a binomial situation where your P is 0.5, your number of trials is 8, and here's your number of successes. Whenever you have a situation where you're given a probability or proportion, you're given a number of trials and X a number of successes, that's binomial. And so we'll do binomial PDF for each of these. And so what I did to find these numbers, so I started out to get to binomial, you go to second VARs, which is distribution, and then you just scroll down to binomial PDF for 1 point. Our number of trials is 8, our probability of success is 0.5, and then the first value is 0. And there it is. So there's the probability that 0 would like it is that. And then I'll just change this to 1. I'll do second entry, which is right above the enter button, second entry, and that enters the last command. Then you just change this to 1. Boom. And so that's the probability that you'll have 1 succeed. If in fact, 50% of the population would like citrus fresh, the probability that you'd only get 1 out of 8 is about a 3% chance. And so I did that for all of this, all the way through 8. Okay. You'll notice it's symmetrical because our P is 0.5. So the probability of 8 is the same as the probability of 0. But anyway, so that's how you do. That is how you do that. Okay. So when testing the hypotheses in part A, Sunshine Farms will conclude that there is a consumer preference if too many or too few prefer citrus fresh. Based on your probabilities in C, is it possible for the significance level, the probability of rejecting the null hypothesis when it's true, for this test to be exactly 0.5? Well, if you look at this, there's no way you could get a p-value of exactly 0.5, because if it's 1, it's this, and if it's 2, it's that. There's no way it could exactly equal 0.5, and so that is so where's that? So no, there is no value in the table above where the p-value equals exactly 0.5, and so that's what you would say there. So so that takes us to E. All right, the preference data for the 8 randomly selected consumers are given in the table below. So here's the results from their, from their study. This is the actual data. So it's actually 2 out of 8 that like citrus fresh. Okay, based on these preferences in your previous work, test the hypotheses. All right, in other words, what we need to do is in essence find the p-value. What is the probability? Now we got in essence a p-hat of 0.25 of 2 out of 8. All right, a p-value is the probability of getting your value or more unusual. So the probability of getting 2 out of 8 or more unusual than that would be this plus this plus this. But the thing about it is, it's not just this. This is a 2-sided test. So it's not just that lower, it's that different or more different. So we would include also the 6, 7, and 8. That would also be just as different from 0.5. And so we would add all of these up, okay? All 6 of those values, this, and that would in essence be my p-value. And that's what I've done here. The probability of getting a sample p-hat this unusual or more unusual is, and I added those probabilities up, multiplied them by 2, that is the p-value. That's the probability of getting a value is unusual as 2 out of 8 or more unusual. And so our p-value conclusion, this p-value is clearly bigger than 0.05. So I do not reject the null. There is not convincing evidence that the proportion, and I restated the alternative, not concluding, there's not convincing evidence that the population proportion of customers who prefer citrus fresh is not equal to 0.5. And then lastly, Sunshine Farm plans to add one of the 2 new fruit juices, either citrus fresh or tropical taste, to its production schedule. A follow-up study will be conducted to decide which of the 2 juices to produce. Make one recommendation for the follow-up study that would make it better than the initial study. Provide a statistical justification for your recommendation in the context of the problem. This is an insanely small sample size. I mean, especially with proportions. So that's what I would say. And why would you want a bigger sample size? It makes you more precise. There's less variability in your results, and you'd be more likely to detect if there really was a difference in the proportion, like tropical taste versus citrus fresh. And so that's what I said. They should use a study. They should use a study that has a larger sample size. This will result in less variability in possible outcomes. This will make it more likely that you'll detect a difference in the preferences for citrus fresh and tropical taste if there really is a difference. And that's it. That is the 2006 Form B. If you got any questions about that, please send them to me. I hope you have a great day.